Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, if you recall, in the last lecture basically we were discussing about the torsion, and there we found out the development of different stress components, okay, for the circular cylinder member when it is under torsion or the twisting moment, right. So, and there already we have seen that all the stress components are 0 except tau theta z, and we have derived the expressions to find out tau theta z and the twist angle and all those things, right. If you go back to the previous lecture, basically you will be getting all those things. Now, today what we will be talking about, we will be looking at the stress analysis in case of torsion. Okay. So, suppose if you look at this figure basically, so this circular cylinder member is under constant say twisting moment mt, and therefore, if you consider any say square element, okay, on the tau theta z or on the z theta plane, basically you will be having only, this is a kind of only pure shear, there is no other kind of stress component available on this element, only tau theta z is acting, okay, on z plane as well as on theta plane, right. So, there is no normal stress acting on these planes. So, now if I try to represent this stress state of stress, okay, with the help of the Mohr cycle, whatever we have learned in sigma and tau space. So, basically it will look like, so if you look at this, so this tau theta z is having the positive sense, that means the magnitude of tau theta z is positive as per our sign convention, whatever we considered earlier. So, therefore, your theta will be corresponding to x axis and z is corresponding to y axis, and so on x plane you are having tau theta z, there is no normal stress. So, that is your theta plane, okay, on the Mohr cycle, and that is your z plane on the Mohr cycle. So, if you complete the Mohr cycle, that will look like this. Okay. So, now if you look at or if you try to find out the major and minor principal stresses, right, major principal stress is sigma 1 and minor principal stress is sigma 2. So, the magnitude of major principal stress and minor principal stress is nothing but tau theta z, that is the magnitude, means I am talking about the mod of sigma 1 is equal to mod of sigma 2 is equal to tau theta z. However, if you look at sigma 1 and sigma 2, so sigma 1 is nothing but your tau theta z, okay, from the Mohr cycle, whereas sigma 2 is minus tau theta z. Okay. This is coming from the Mohr cycle. Now, what you are getting from this, so tau theta z is nothing but basically the magnitude, okay, now the magnitude. So, this much of, this is the radius, okay, radius of the Mohr cycle, fine. So, now if you look at this, so sigma 1 is giving you the tension, that is the major principal stress is giving you the tensile stress, whereas the minor principal stress sigma 2 is giving you the compressive stress, and that can be shown like that. So, if you try to rotate the axis, because now another thing is that between theta axis and major principal stress axis, that means theta and 1, right, this axis is making an angle 90 degree on the Mohr cycle. So, therefore, in the physical plane, that means here it will be making 45 degree. So, this is your theta direction and this is your sigma 1, okay. So, one direction, okay. So, 45 degree, fine. So, now here sigma 1 is acting, and which is tensile in nature, and sigma 2 is acting on this plane which is compressing in nature. Now, if you look at this configuration, okay, so along this line AB, okay, along this line AB, whatever plane is lying along this line AB, on that plane basically your sigma 1 is acting. That means your major principal plane is nothing but along the line AB, on which the maximum tensile stress is acting. Maximum tensile stress is nothing but your sigma 1. Similarly, the plane, this plane, okay, on which your compressive stress is acting, and that is pure compression, right, that is your sigma 2. Now, you might have seen, okay, in several instances where suppose you are having a very say some your Coca-Cola can or Pepsi can, you might have seen, and if you try to give the twist, okay, it will warp in particular direction. Okay. So, why it is happening like that? Have you ever thought about that? It is something like that. If I do the similar kind of experiment with this chalk, the chalk, you know, the chalk is a brittle material as per our previous definition. The chalk is a brittle material. It is very weak in tension, but it is very strong in compression. So, now what I am doing, I am just holding the chalk, there is no other force acting on this chalk, and I am just giving the twist. Okay. Now, you see, now if you look at, this is the plane, okay, this is the plane on which, or rather this is the plane, whatever, I mean this is the lower part and this is the upper part. So, this plane, I mean it has not got the failure or the rupture along the cross section, rather there is some angle, okay, along which, so this is the angle of the plane. That means, if you look at this figure, so as I told you, this chalk is weak in tension. So, on this plane there must be some maximum tensile stress happened, and therefore, this plane is becoming more vulnerable plane, and that is why it is breaking or the failing on this plane, right, and that plane is nothing but your plane parallel to line AB. Understood? So, now if you do this experiment, this is very simple experiment. So, this chalk will be several times you do it, you just give pure twisting moment, you will be getting always failure like that, okay, and that is basically telling that because of chalk is weak in tension, and you must expect the failure in the chalk where the maximum tensile stress is acting, and the maximum tensile stress is acting on this plane, because this plane is nothing but your AB plane, as I showed in the figure. Similar kind of example or similar kind of thing you can do with the help of your Coca-Cola can or the Pepsi can, right. You just, because that is very thin sheet, right, the can is made of very thin sheet. So, if you give the twisting moment, you will see the failure, okay, along the plane on which the maximum tensile stress is acting. Similar kind of thing you might get, say suppose you are making some cylindrical very thin cylindrical say member, slender member with the help of paper, and you give pure twisting moment. If you give that, the paper will be folded or will be say warping, okay, along a particular plane on which the maximum shear stress is acting. So, this is the reason, okay, you might have experienced that thing, you might have seen earlier, but you never thought that why it is happening like that, why it is following that kind of plane on which you are getting this warping, right. Now, you know that why it is happening like that, because in case of torsion the maximum tensile stress will be occurring on this inclined plane which is parallel to line AB. Okay, fine. Okay. Now, we will come back to the yielding characteristics happened in case of torsion. Okay. The onset of yielding in torsion. Now, in the previous figure you have seen that if I try to get the Mohr circle for the state of stress developed in torsion, so that will look like this, right. So, this is my sigma tau axis, sigma tau, and this is the Mohr circle. This is 1, 2, and this is your z and theta, right. I am just reproducing the previous figure whatever we just have seen. Okay. Well, so now your, as we have written, sigma 1 is nothing but tau theta z, sigma 2 is nothing but minus tau theta z, okay, because this is your tau theta z. That is the radius of the Mohr circle, okay, and sigma 3 is obviously 0, because we are talking about the planar stress, right. So, sigma 3 is 0. So, now if as per your Mises criterion, so using the Mises criterion, your y, that you know, that is your yield strength, okay, is given by this equation. Already we have derived that, half sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, right. Already we have seen that. This is your von Mises criterion, okay. So, as per that, if you put the values of sigma 1, sigma 2, sigma 3, whatever you have got here, so you will be getting half 2 tau theta z whole square plus minus tau theta z whole square plus minus tau theta z whole square. Okay. So, from this I can get tau theta z is equal to 1 by root 3 y, that is nothing but 0.577 y. This is as per Mises criterion. That means, if your yield strength of the material, so the material with which the circular cylinder member is made of, okay. So, if the yield strength of the material is say y, okay. So, you can go up to maximum this much of shear stress, okay, to avoid von Mises, I mean to avoid the failure as per von Mises yield criterion, okay. Now, let us see what is happening with the maximum shear stress criterion, whatever we have learned earlier. So, let us talk about that. As per maximum shear stress criterion, that is your Tresca criterion. So, using maximum shear stress criterion, okay, your sigma max that is your shear stress criteria, maximum shear stress, sigma max minus sigma mean by 2 is equal to y by 2. That was your maximum shear stress or the Tresca criterion, okay. So, what is your maximum value of sigma, that is sigma max, that is nothing but tau theta z, that is nothing but your sigma 1. Now, here what is the minimum value of your sigma, that is nothing but your sigma 2, that is minus tau theta z. So, minus of minus tau theta z So, this gives me tau theta z is equal to y by 2, that means 0.5 y. So, that means in case of Horn-Mises or the Mises criterion, how much you are getting tau theta, if tau theta is becomes equal to 0.577 y, then you are getting the yielding. Now, if you look at the maximum shear stress criterion, as per that, when theta z is reaching 0.5 y, okay, basically, then you are getting the yielding. So, this as per maximum shear stress criterion, you are getting much lower value of tau theta z to initiate your yielding. So, therefore, we can you can see that you can get it, you can write down torsion involves a stress state which gives rise to the maximum discrepancy between the two criteria, two yield criteria rather. Two means one is von Mises and Mises, another one is maximum shear stress, that is nothing but your Tresca, okay, and which is 15%. This gives the maximum discrepancy. That means, if you go by Mises criterion, or if you go by your maximum shear stress criterion, so and if you compare this both the criteria basically, then basically you are getting the 15% discrepancy, okay, between these two failure criteria, okay, that is happening in torsion, okay. So, in one case you are getting 0.577 y, in another case you are getting 0.5 y, and that gives the discrepancy between these two criteria. So, with this I am concluding your torsion chapter. Now, we will take a couple of numerical problems and then we will move to the next chapter. Okay, so, let us take some numerical problem. So, problem 1, a hollow sheet hollow steel shaft, okay, 2.5 meter long, must transmit a torque of 25 kilonewton meter. Okay. The total angle of twist over the length of the shaft is not to exceed 2 degree, and maximum allowable shear stress is 82 meganewton per meter square. Find the dimensions. Find the dimensions of the shaft that is inside and outside diameters. Okay. Given is G equal to, that is the shear modulus is given as 80 giganewton per meter square. Okay, so this is the problem. So a hollow steel shaft, this is a hollow circular shaft, whatever we have discussed earlier. So hollow steel shaft 2.5 meter long must transmit a torque of 25 kilonewton meter. The total angle of twist over the length, that means from the bottom, if you compare from the bottom to the top, the total over the total length, the twist angle is not to exceed 2 degree, and maximum allowable shear stress is 82 meganewton per meter square. So these are your limits. Okay. Find the, I mean you are basically going to design this kind of shaft under this restriction. So the total twist should not exceed 2 degree and shear stress should not exceed 82 meganewton per meter square. So find the dimensions of the shaft, that is inside and outside diameter. Okay. So that is nothing but your shaft. So you are going to design that, where G, that is your shear modulus, is given as 80 giganewton per meter square. So let us solve that problem. Okay. So let your inside diameter equal to say di and your outside diameter say do. Okay. So now, and your length, that is also not given. So length we are considering say L. So as for our derivation, whatever we have done earlier, so the twist angle is given by MT L by G I Z, if you recall, right, no issue. So here actually we can put, because our restriction is 2 degree, that is the maximum twist we can have in the shaft. Okay. So 2 into pi by 180 radian is equal to MT. Okay. MT is nothing but the torque applied, that is given, that is 25 kilonewton meter, and L is given 2.5 meter long. Okay. Then L is given as 2.5 meter long. Okay. And G value is given as 80 giganewton per meter square. So that is nothing but 80 into 10 to the power 9 Newton per meter square. So this 25 into 10 to the power 3 is basically Newton meter. Okay. And IZZ, because you do not know the dimension, so you cannot find out the polar moment of inertia. So IZZ is not known to you. But however, from this numerical values you can find out IZZ, which will be coming as, from this I can simply get IZ equal to 2.238 into 10 to the power minus 5. Okay. That is your meter to the power 4. So equation 1. That is the value of your. So you need a shaft which will give you this much of IZ, okay, to satisfy other parameters. Okay, fine. So from shear stress, your tau theta z is equal to, as you know, MT R naught by IZ, okay, which can be written as in terms of your diameter d naught. R naught is the outside radius. Okay. So d naught twice IZ. Fine. So here your upper limit of shear stress which is getting developed in the shaft, that is given in the problem, that is nothing but 82 into 10 to the power 6, okay, meganewton per meter square, is equal to 25 into 10 to the power 3, that is Newton meter, that is a twist MT, and D naught obviously is not known to you, DO rather, DO is not known to you, and 2 into Iz is now known to you from equation 1, that I am putting 2.238, okay, into 10 to the power minus 5. Okay. So, from this I can find out DO is equal to 0.1468 meter, that is nothing but 146.8 millimeter. Okay. Now, you have got at least the outside diameter of the shaft, and you know the polar moment of inertia of the shaft. So, from that you can find out the other dimension, that is the inside diameter of the shaft. So, that means from this is the expression for Iz of a hollow circular shaft. D already we have seen that, and you know from your earlier say knowledge, okay, 2.238 into 10 to the power minus 5. Okay. So, from this you will be getting Di, because now DO is known to you, that is given here. So, Di can be obtained as 0.124 meter, and that is nothing but 124 millimeter. So, you need a hollow circular shaft, okay, to satisfy the conditions. This is your inner diameter 124 millimeter, and this is your outer diameter 146.8 millimeter. Okay. So, this can be used, which will satisfy all the limiting conditions, like your limiting condition of the stress, shear stress, limiting condition of your twist, and all those things will be taken care if you choose hollow circular shaft like this. Okay. So, I will stop here today. So, in the next lecture we will be taking one more numerical problem, and that will be basically concluding this chapter on torsion. Thank you very much.